So in our last example here, we have to find at least one non-zero solution to the differential equation y double prime plus 6y prime plus 9y is equal to 0. So just like all the others, we start out with a characteristic equation. So that means we convert the y's into r's and the derivatives into exponents. So r squared plus 6r plus 9 is equal to 0. And that actually factors as a perfect square. That's r plus 3 squared is equal to 0. So our roots here, we get a double root. R is equal to negative 3, and then our other root is also negative 3. So we really only get one root from that. So we have a solution here. Y is c1e to the negative 3t. But we can't find a second solution because our other root is also negative 3. So let me write that down. But we can't find a second solution that is independent of our first one. That is independent of our first solution, which was e to the negative 3t. Now I left a little space here after the word can't because this is actually the subject of a later lecture. So I'm going to say we can't, I'll put that in red, we can't yet find a second solution because a couple lectures later we'll figure out what to do with repeated roots. But in the meantime, we don't know how to solve that. I will say a common student mistake would be to write the general solution as, well, if you just kind of blindly look at these two roots, you would say c1 e to the negative 3t plus c2 e to the negative 3t, because you just copy your two roots into the exponents here. So if you wrote that, that would be incorrect. That is not the general solution. And the reason is because you really have two copies of the same solution there. You need to find a second independent solution. We haven't learned how to do that yet. So in the meantime, all we can offer as a solution is just the c1 e to the negative 3t. So there is another way to solve these equations with repeated roots, and we'll learn how to do that. We'll learn how to solve this in a later lecture. So you have to peek at the lectures a couple more lectures down the line, and you'll see one called repeated roots. And that's when we'll learn how to find a second independent solution to an equation when we do have repeated roots. So just to recap here, we started out with the characteristic equation where we converted it into a polynomial in R with exponents instead of derivatives. We factored it down just like the others. We found the roots. And then the new wrinkle in this example was that both the roots were the same. We had the same root. So we were able to form one solution, c1 e to the negative 3t, but we can't find a second independent solution, so we can't tack on a c2 e to the negative 3t because that would just be a copy of the first solution. So in order to find a second solution, we're going to have to come back and study this in more detail on our later lecture on repeated roots. So that's the end of our lecture on distinct roots. We'll come back later and start talking about complex roots and repeated roots. These are the lectures on differential equations. My name is Will Murray, and you're watching Educator.com. Thanks.